Good afternoon, everybody. Can you hear me? I guess. So, thanks for giving us also the chance to talk about toxicity, effect, and non-animal methods for testing PFAS in the water cycle. At first, please let me thank all my colleagues. So, at first, Mikey Liu and Anis Saravich and Matthias Zessner, which have been involved in the case in Vienna. So, they were preparing the water samples and sent to us. Then also my colleague Harry Besseling, who is responsible for the analysis of the different bioassays, and also Anita Sosnowska and Enrico Mobelli, because they have used our in vitro data and the risk in silico modeling, how many PFAS are active in our bioassay. So this is a combined team effort here, because it's a biodetection system. It's how we involved with the Institute for Water Quality and Resource Management in TÜbingen, KUSA Lab in Gdansk, and in Eres in Verneuil et Halate. We have three options. Yeah. Okay. So of course, if you think about toxicity, there are many publications about toxicity of PFAS. Today, I will focus on non-animal testing, so in vitro testing. And if you look at the literature, you will find there are known effects from the PFAS for the thyroid diseases, for breast cancer, testicular cancer, and obesity. And of course, this is in humans. Of course, we want to work with more ethical methods, so non-animal methods. So we are working with human cell-based protein assays, and you can see the table here that for this case we are using different key events. One is the thyroid anti-agonistic effects. One is the transthyretin receptor binding, which is a transport protein. And here the PFAS are competing with T4. So it's about how the PFAS are transported from blood to over the blood-brain barrier. And this can be inhibited by the PFAS. And we'll also have a look at the estrogens, the female hormones, and also the inhibition of the male hormones and the androgens. And also we look at the obesity or metabolic disruption. So in the PFAS project, we have three different phases in the project. The first is where we selected together with the chemical analysis laboratory 45 PFAS, which we will try to do by chemical analysis, but also by the bioassay. So we have chosen different kind of toxicity testing, so cytotoxicity, genotoxicity, oxidative stress, then the H receptor activation, so dioxin-like part of the pH, and a lot of the different endocrine disrupting properties and obesity. The aim is here, because if you have non-animal testing, you can test very quick many PFASs, and if you say P4 is the most toxic one, then you can give new relative potency factors. So you can say how toxic compounds are compared to before. And this we have done with this panel of bioassays. In the second period, we were looking, okay, how many of the PFAS are active in the bioassay, and in the last period, we were using this bioassay for testing complex mixtures of hundreds or maybe even thousands of PFAS, for example, in water, soil, and sediments in 5 different case studies. And today I will show you only the case from Vienna, because the Berlin, Ancona, Bessos on Orleans site is still under investigations. So this bioassay offers you that you can test a complex mixture of known and unknown PFAS. Please again understand, if I look at the US EPA database, there are about 15,000 PFAS. I say it again, it's 15,000 PFAS. And if you look at the chemical analysis, often we hear about 20 or 22 or 24 PFAS. So again, if you calculate 15,000 minus 24, you are at 14,978 or 76, just to get the number right. And this is only about, we are only talking about the flow layer. We are not talking about any kind of transformation products. We are not talking about metabolites in human, rat, or animals. And we are not talking about polyhalogenated PFAS. So the number will be even increasing the following 10 years, I can promise you already. So the question is, how can we create a serotoxicity umbrella, and how can we combine state-of-the-art technology to do that in an effect-based manner? This we tried in the last 2 years. So how we are doing this? So we are one of the global leading laboratories for endocrine disrupting chemicals. So of course we are high throughput, so we have an automatic cell seeding robot, then we add the sample in different concentration, and then we have a ruminator with a stagger robot. So the idea is, of course, if you really want to have serious toxic-free and zero pollution in the Green Deal, then you need, of course, tools for covering in a non-animal manner the unknown PFAS, and you need also some who covers the sources of PFAS. It's of course very important that you have low-cost alternative non-animal testing, because I think it's very clear that we cannot test the 50,000 PFAS with animal testing in the next 50 years. So we need alternatives for that. That's why ours is a high throughput. We can test about 50 samples per week per person with that. And therefore, if you also integrate in your testing strategy such effect-based testing, you will of course increase capacity for such total PFAS analysis tools. And of course, we combine always chemical and biological analysis to know which are the drivers in the PFAS toxicity. So this was then in phase 1. You don't have to read it, what it just says. On the left side are many PFASs. So we designed in this case 45. At the top, you see different names. So cytotoxicity means cell death. Then the next one is NRF2, which is oxidative stress or steam sensitization. The next PPR alpha is obesity or metabolic disruption. And then we have anti-PPR gamma, which is the inhibition of that metabolic disruption. Then we have the disruption of the thyroid hormone, and we have the TTR bioassay, which is the competition from PFAS with the T4 hormone. And on the last slide, you have a proposal from a European document called 540/2022, where they have basically from animal testing read across, they established some relative potency factors. Now, if you look in detail at this, you will see that the in vitro test and non-animal testing has very similar toxicities like animal testing. This is very good news, of course. But you will also see that some of the molecules which you have tested in the bioset are not yet tested by the animal testing, and also are often not used in the chemical analysis, like P37-DMOA. If you look at the literature, it's in the bicarbonate accumulated, so it's certainly a very toxic compound because it's also ecotoxic relevant. And this is here the most toxic compounds in the TTR bioassay. What we also see is, if you look, for example, at GeneX, that this compound is more active as a metabolic disruptor. So we would use here the PPR alpha bioassay for this kind of compounds. So in the promisces project, we are the Umweltbundesamt, the German EPA is our partner laboratory. We have trained them 2 or 3 years ago. This bioassays, they have their own bioassays, so they have a second batch of bioassays, also for cell test, cell death, genotoxicity, oxidative stress, estrogenicity, and so on. And they have here, they made a poster presentation last year in the PFAS conference, where you see in the conclusion and outlook that based on the results in testing single substances PFAS, effects can be measured for an interaction with the estrogen, the female hormone, the inhibition of the male hormone, and the TTR. And it's a clear prioritization can be made favoring the TTR or PFAS colors. So we'll focus on that bioassays in the coming 10 minutes. Already in 2020, the German EPA gave us the order to test these 30 PFAS, and we published this also in Environment International. If I look at the new data that I just showed a second before, they're very similar. So we have now 2 different data sets from PFAS compounds, which we have the same results of toxicity, which is also good news. Now, as I mentioned before, in the phase 2, Imeris and Kusa, that they used our in vitro data and put it in different in silico models. Now, for the in silico model, they had 12,654 PFAS, and from that, they had about 8,400. They had details what they can use for in silico modeling. Now, if you look at our TTR data, 7,685 were active in the PFAS colors or in the TTR node. So this is very important. So we have now a testing technology which can cover thousands of PFAS. Now, if you look at how toxic they are, you can use the MLL model. In this case, you see that 1,283 have higher relative potency factor than 0.1. And 150 compounds are even more toxic than before. If you use a more traditional approach, the MLM approach, you will have less numbers, so it's still 1,057 active in the TTR, and more than 119 compounds have a higher relative potency factor than 0.001, and more than 40 are more active than PFAS before. So now we are applying the bioassay on surface wastewater. What we have to do there, what we have to do there to do that. Not too fast, there's a time between the time you touch and interaction. I see it. It's very sensitive, sorry. Yeah. So what we have to do is first we do, if you get 1 liter water, you have to get, of course, down to a few microliters, what we use in bioassay. So we use a wax SPE extraction. It's just a traditional technology where also chemists use. So we focus on that PFAS which are bound on the wax cover. And this we put it later in BDS and we clean it up. And then we put this 50 microliter on the PFAS colors. Just now we are entering our water testing. I would like to inform you that there is a ISO standard 23196 from 2022, which describes how to calculate biological equivalence concentration for bags. So I will in the future, in the last few minutes, I will always refer back means the analysis of the bioassay. While TEC and SEC is called for the chemical analysis when we convert it to chemical concentrations. I will show you in a second if this machine works. So in an earlier publication of mine, this is difficult to read, but what it means is basically you only have to look at the bottom. It says the cumulative effect-based trigger value. Now, if you look at the common guidelines, more or less in the Water Framework Directive and in the food guideline, there's no, they just all the 24 or 4 PFAS, they use them as total sum or a sum of PFAS, but they don't tell that, for example, PFAS is more toxic, so you can have less concentration of that molecules compared to PFBR, which is less toxic, so you can have more of that component. So the only guideline which has really makes a difference in the concentration and therefore the toxicity is the German Bundesgesundheitsstatus for drinking water. So I use their concentration and I multiply with the potency factors from the animal testing from the Dutch government or the European 540 2022 guideline, and also with our relative potency of the bioassay. And so the animal testing has some different relative potency factor, but in general, if you sum them up, then you would have an effect-based trigger value between 3 and 4.6 microgram P4 equivalent per liter water. So it does not matter so much if you use animal testing or animal testing, non-animal or animal testing, the relative potency factor have nearly the same effects. But this would be effect-based trigger value how I would evaluate water testing. Now I would like to come at our first second promises. As I mentioned before, with the Technical University in Vienna, we were testing river water, municipal wastewater treatment by effluents, industrial wastewater treatment by effluents, and influent stormwater. Now, as you see on the bottom, you see the chemical analysis. So in this case, the chemical analysis could identify 21 PFASs from the 42. And now we can convert the chemical concentration with the relative potency factor, and we have then chemical converted microgram P4 equivalent to liter water. And then we measure the same water sample with the PFAS colors, so the TTRT colors, and then we can compare those. So what you nicely see here is that the river water has the lowest level, and the highest level, I would say, has the influent stormwater. But the nice thing is, in that case, what you see here is that if you use the effect-based trigger value of 3 microgram P4 equivalent to liter water, then all those samples are below there. And this, of course, really good news for that case.
1 minute.
Yeah, but let me show us other cases, like, for example, this one. So this is from the Netherlands. We published this last year. So this is here in Netherlands, surface water, drinking water, and wastewater effluents. So you see on the right side, if you look at the orange band, you see the wastewater treated by influent is a level of 250 on both water treatment plants. Luckily, the wastewater treatment plant, if you the effluent, is around 5. But this is still above the surface water drinking water. So here still you can see the drinking water plant works quite well, but still I think we should get lower than the 3 microgram. This is the next study from Austria, from the Umweltbundesamt. So they also have established the PFAS colors. And here they use also the chemical concentration, some of PFAS, P4 equivalents, and then they compare to other bioassays. And you see here the levels. If you look at the bioassay, they are between 1 and 15. But this is about 5 times higher than